Hi, in this video lecture we are going to deal with AC load line analysis. So our aim is to understand the concept of AC load line and to calculate the maximum symmetrical swing of your output signal. So what is the maximum signal I'll be able to get as an output? Okay, so that is what we are going to discuss here. So AC load line analysis. So you would have already done the DC load line analysis. In case of your biasing methods, we would plot what is the maximum current, what is the maximum voltage, and we will connect those 2 points. We get the DC load line. Okay, so your DC load line will be the slope of your DC voltages and DC output voltage, that is VCE by IC. So that would have been your DC load line. Similarly here, to get your AC load line, so we take up the AC equivalent circuit and we'll write the KVL to the output and we get the relationship between the variation in your VCE and IC. So for this, to explain this concept, I have taken a simple bias connection where the self bias is being modified with an RE1. So this circuit already we have analyzed. Okay, we have did the small signal analysis for this circuit. So I am taking up the same circuit to do the AC load analysis. Okay, so that you can get the concept of this a better one. So here you have at the emitter RE resistor as well as your RE1 resistor. But RE1 resistor is been bypassed by a capacitor. So now when I draw the AC equivalent circuit, this will not be having any effect. But when you do the DC analysis, then because for your DC analysis, your capacitors will be open circuited. So as you open circuit this, your RE and RE1 both will be providing the impedance at your emitter terminal. But when you do the AC analysis, since this has been bypassed, you will have only the effect of your RE. So I have drawn the AC equivalent circuit. Here you could see that I have short circuited your bypassing capacitor. So now we take up this to analyze. Okay. So now we apply KVL to this loop. So when I apply KVL to this loop, you get it is VCE plus IC times it is RC plus RE is equal to 0. If you would have done the DC analysis, then this would have been the slope. You could have seen that in case of your DC analysis, if you apply KCL to your output loop, your VC would have been VCC minus capital IC into RC plus RE plus RE1. So the slope would have been minus 1 by RC plus RE plus RE1. But when you do the AC analysis at the output loop, there is no RE1 effect, only the RE effect is there. So VCE plus IC into RC plus RE is equal to 0, or the slope becomes it is minus 1 by RC plus RE. So now let me plot both this slopes. Okay, so I have taken an example here. So here the DC load line slope is given as minus 1 by RC plus RE1 plus RE, and AC load line slope is given as minus 1 by RC plus RE. So this is now the operating point which has been fixed. So now our aim is to find out. What is the maximum symmetrical swing. You can get it as your output signal. The maximum current here it is provided. Okay. The maximum current here provided is 0.33. And the operating point is being set up at 0.2 milliamps. Okay, so 0.2 milliamps. Now you can make your signal, your collector current to vary from 0.2 milliamps in the negative axis up to 0. Okay, in the negative axis up to 0. But on the positive axis, if you allow it to make it to go through the same symmetrical swing, so from 0.2 to 0, it means 0.2 milliamps. So similarly, if I allow it to make a positive swing over 0.2 milliamps, it becomes 0.4. But maximum operating current is given as 0.33. So then part of your signal could be clipped off. Okay, part of your signal could be clipped off. So therefore that value we cannot choose. So maximum we can have only 0.33. So from 0.2 it can maximum swing up to 0.33. You cannot go beyond that, because if you go beyond that, your signal will be getting clipped off. So it is only 0.13 milliamps you can swing. Or even if you want to make a restriction on your maximum current, you don't want it as 0.33, you want to restrict it to 0.3, then you can have it is only between 0.3 and this is 0.2. So it is only 0.1 milliamps you can make a swing. So you can restrict what is your maximum current, what is the minimum current. Okay, so based on your slope line, okay, based on your DC load line, you can find out. Okay, you can find out what is the maximum current you can allow, what is the minimum current you can allow. You can make a threshold, because when it operates nearer to your cutoff, then your signal, okay, if it slightly increases also, your signal would have been clipped off. So you have to take care of that. So we'll restrict some limits somewhere here, your IC minimum somewhere here. Okay, and then similarly my IC maximum, I'll keep it up somewhere here. So then we can find out. So for a perfect that is symmetrical swing, both positive cycle and negative cycle has to undergo the same amount of change. So if I restrict it to 0.3, then it becomes 0.1 milliamps on the positive cycle. Then similarly I can have it as 0.1 milliamps on the negative cycle. So that is up to this much. Okay, so now my VCE will be equal to, so in previous slide we have given the equation, your VC is equal to minus IC times it is RC plus RE. So substituting this collector current now, so the collector current now can maximum have a swing from 0.3 to 0.1. So it is 0.2 milliamps. Okay, 0.3 difference 0.1. So it is 0.2 milliamps times it is RC plus RE. That will be your voltage swing. Okay. Thank you all.